Hello and welcome to today's lesson on fission reactors, which is part of the atomic structure topic in GCSE Separate Science physics. So in today's lesson we're going to try and understand how a power station can carry out the fission process. So if we've been successful and learnt in today's lesson, we can explain how a fission reactor works, describe the parts of a thermal nuclear reactor, and explain how a nuclear fission reactor is controlled, which forms part of the GCSE Separate Science physics specification 4.4.4.1 nuclear fission, which is a separate science only piece of content. Now, to understand how fission works, we've got to understand the complete process. So let's consider one unstable uranium nucleus. Now, throughout this process, please refer to the particles as nuclei, because nuclear fission is a nuclear process. It only involves nuclei. This process does not involve atoms or ions or isotopes or particles or molecules. It's only nuclei it affects. Now, a neutron is fired to this uranium nucleus and the neutron is accepted into the nucleus. The neutron will then be accepted because there's no repulsion, because it's got no charge. Now, the neutron will induce fission. So we call this idea induced fission. Now, on rare instances, nuclei can fission naturally. This is called spontaneous fission. So for the neutron to be accepted by the nucleus, it must be traveling at a particular speed. Too fast, it would smash straight through the nucleus. Too slow, and we'll be able to get close enough to the nucleus. So it's got to be going at just the right speed. But the addition of the neutron to the nucleus makes the nucleus extremely unstable. So the added neutron increases that instability factor in our nucleus. So what happens is we've got an even more unstable uranium-236 nucleus. So this uranium nucleus splits into two smaller nuclei, and the smaller nuclei are more stable than uranium. So what happens is we've increased our nuclear stability. But this process will also produce a lot of energy. Per kilogram, there's 1,000 times more energy in nuclear fission than there is in combusting coal. So what happens is we release energy to the surroundings. So the excess potential energy is shed by the nucleus and given off as energy. So what happens is mass from the original uranium nucleus is turned into energy, and this is equivalent to the mass lost in the process. So the energy released to the surroundings is calculated with our equation E equals mc squared. So the energy was released in the form of the kinetic energy of the products, but also as gamma rays as well. So what this means is the different particles produced in the fission process will move off at high speeds, smash into other particles and transfer their energy, heating things up. So the mass deficit produced by fission, the mass that has changed, is released as energy to the surroundings. Now, it is this energy that's released in fission which is used to heat up water in nuclear power stations. Now remember, the energy released in fission is found initially in the form of kinetic energy of the products in this particular event, but it's also found in the form of gamma rays as well. So there's actually going to be two forms of energy released in the fission process. And again, we can work out how much energy is released with our equation E equals mc squared. Now, there's a lot of energy released per kilogram, so that means that one fission event will produce little energy via this process, but there are so many uranium nuclei fissioning all at once, you produce lots of energy. Now, the fission process also produces 3 neutrons in its splitting process too. Now, this is important as the fission process is linked together, and we call this a chain reaction. Now, it's important to note that only uranium-235 will fission. Any of uranium-238, a different isotope, will not fission. So this means the greater the amount of uranium-235 in our sample, the greater the amount of fission that can carry out in uranium. Now, we can artificially increase the amount of uranium-235 in a substance. We call that enriching uranium or enriched uranium. Now, if a neutron encounters uranium-238, it can be absorbed and you just get uranium-239, and there's no more of the fission process that takes place. Now, what happens is at each stage, the mass deficit releases energy per the fission event. So because mass has turned into energy, at each of these processes, energy is released. Now what happens is each fission reaction releases neutrons that are used in further reactions. So each fission event releases energy to the internal energy that surrounds by E equals mc squared. And what happens is because each fission event releases 2 or 3 more neutrons, these neutrons can fission further uranium-235 nuclei. So we've got a chain event, a chain reaction. Now just note these neutrons have to be slowed down to ensure they don't smash through any nuclei, because they've got lots of kinetic energy when they first get released in the fission process. Now some of the uranium will be absorbed by the nuclear neutrons will be absorbed by uranium-238 and can actually make plutonium as well, which can also fission, but that's quite a high level event. Now let's consider a fission power station. So the nuclear fission process takes place in a steel vessel which we call the nuclear reactor core. So this means we've got to consider the processes that take place inside this steel vessel. So if we understand the fission process in this fission generator, we can understand how a nuclear power station works. So let's consider what happens if the fission rate if we have just a standard reaction. In an uncontrolled chain reaction, there's been no measure taken to change the fission rate. So what happens is because each fission event releases 3 neutrons, which can then go and fission other uranium nuclei, your amount of energy released increases very quickly. So 1 neutron is released, that can lead to 3 neutrons, to 9, to 27, to 81, and the number of a fission event changes at the same rate. So what happens is the energy per second is increased in how much is being released every time we have this part of the chain. So this will eventually cause an explosion, which is a nuclear weapon. Now this is what we call an uncontrolled chain reaction. The chain reaction has gone supercritical. At each step of the fission chain, the fission events are releasing a greater amount of energy because there's more fission events taking place. Now what happens is when the energy released is large enough to melt the uranium fuel, we say the chain reaction is in meltdown. Now it's important to note that if we have an uncontrolled chain reaction like in a nuclear weapon, this means the fission rate increases exponentially, and this will happen naturally after the process has been induced and nothing has been done to control this chain reaction. So if we want in a power station to have a controlled chain reaction, we must ensure the number of neutrons fissioning uranium nuclei stays constant. We want our fission rate to stay constant. We want our chain reaction to be critical. Now what we do if we have this idea is that in the nuclear power station we will have a steady release of energy. The process has gone critical. Now the mass of uranium needed to do this is called the critical mass. Now the idea that a chain reaction is critical is actually very good. Now all the engineering in a power station is to ensure you get a critical chain reaction, a controlled chain reaction. Interestingly, we don't cover this in much detail at GCSE, but if measures are taken to stop the chain reaction process, all of the fissile neutrons will be stopped from encountering uranium, and if this happens in a nuclear power station, the fission process stops and no more energy is released. We say the process, the chain reaction, has gone subcritical. Now this is what happens in a power station if the plant goes into an emergency shutdown. So the fission rate ceases. So what are different types of chain reaction? We've got our supercritical chain reaction, which is where the fission rate increases exponentially. Now how is this achieved? You just allow a induced fission process to take its natural course, and then eventually if you have a supercritical chain reaction, enough energy is released to eventually cause nuclear meltdown or for a nuclear weapon. If you have a critical chain reaction, the fission rate remains constant, and you can do this by placing something called control rods into the reactor vessel, and you'll get a constant supply of energy released in a power station. Now if you have a subcritical chain reaction, the fission rate decreases to 0. Now you can achieve this by placing the control rods fully into the reactor vessel. The chain reaction ceases and you get no more energy. Now like we said before in the lesson, the fuel rods in the reactor core contain 2 different isotopes of uranium. Now naturally only uranium-235 will fission when it absorbs a neutron. Uranium-238 will not fission when it absorbs a neutron. Now natural uranium found in the ground, only contains 1% of uranium-235. So the greater the amount of uranium-235, the more fission that will occur, the more chance of a chain reaction development. Now, physicists have developed enriched uranium to ensure a chain reaction is produced in the reactor. Now, enriched uranium contains about 3% uranium-235, which is still a very small amount, so therefore it takes a long time to carry out the enrichment process. As an aside, the fission bomb contains 50% uranium-235, which is why it can take a very, very long time to actually produce a fission nuclear weapon. Now, many countries wish to develop the ability to produce enriched uranium. However, many developed countries do not like to share how this is produced, and enriched uranium tends to be produced at secure locations in the country. Now, we need to enrich the uranium fuel until it reaches a critical mass. Now, once you have reached a critical mass, a sustained chain reaction can take place in your reactor vessel. Now, how do we ensure that the chain reaction stays critical and doesn't go supercritical and cause an uncontrolled chain reaction and therefore lead to a nuclear weapon? Well, there are three main features of nuclear reactors in a power station which maintain a steady fission rate with a critical chain reaction in the reactor vessel. The first one is this idea of a control rod. Now, a control rod in the core absorbs extra neutrons, and this keeps the chain reaction under control. The depth of the rods in the core can be changed to maintain a steady reaction rate. Now, we generally make them out of boron because they're really good at absorbing excess neutrons, and these control rods become radioactive waste after the fission processes take place. So in your reactor vessel, you've got two types of rods. The fuel rods, which contain enriched uranium, which tends to be uranium oxide. Now, in these rods, the fission process takes place. You've also got the control rods, which are made from boron, and this is where the neutrons in the process are absorbed. Now, for every fission reaction, on average 3 neutrons are produced. So if you want a controlled chain reaction, only 1 neutron can be allowed to carry on the fission process. So therefore, the control rod absorbs on average 2 out of every 3 neutrons. So what happens is 2 of the neutrons produced in fission are absorbed by the control rod, leading to 1 of the neutrons going on to carry out fission. Now, the depth of the control rod is automatically adjusted to keep the number of neutrons in the core constant, so that exactly 1 fission neutron per fission event goes on to carry out another fission event. So this condition keeps the rate of fission energy constant in the nuclear power station. Now, if you wanted to, you can lower your control rods further into the fuel rods to absorb more neutrons and reduce the amount of fission occurring. So therefore, some of the neutrons could leave the reactor without interacting, and some can travel too fast, and others are absorbed by uranium-235. And if we need more neutrons, we can raise the control rods. Now, as a result, an emergency shutdown procedure of a nuclear power station is to fully insert the control rods into the reactor vessel. This will ensure all the neutrons are absorbed and no further fission can take place. This would cause a chain reaction to go subcritical. So this makes the control rod radioactive after use, so we've got to bury the control rod as nuclear waste after we've finished with it. Now, the absorption of neutrons increases the neutrons in the boron nuclei, makes them unstable, giving us our control rods, which are radioactive. As well as that, in the nuclear power station reactor vessel, you've also got a coolant. Now, the water acts as a coolant in the reactor core, so what happens is the water gains kinetic energy from those fast-moving neutrons and the fuel rod. So what happens is, as we mentioned before, the fission fragments produced have a very high kinetic energy, so they move very quickly once the fission processes take place, so then hit into the coolant, so the fragments then released via nuclear fission collide with the coolant molecules. This transfers their kinetic energy from them to the coolant molecules, and this prevents the reactor core from overheating and causing a uranium meltdown. Now, in older power stations, the coolant molecule actually tends to be carbon dioxide molecules. In newer power station, it is now water molecules. Now this transfers the energy out of the core and heats up water to produce steam, which you can then use to actually produce electricity. The last thing you need to be aware of is a moderator. Now the fission neutrons can be slowed down by collisions with atoms in the water molecules, the coolant. Now this is needed because fast moving neutrons don't cause further fission of uranium. Now too fast and the neutrons smash through the nucleus, too slow the neutrons will not be accepted by the nucleus. So the water is a moderator because it slows down the fast neutrons to just the right speed so they'll be absorbed by those uranium nuclei. So if the neutrons are going too fast or too slow, you will not get absorption in the fission process, so they go at just the right speed. So the fission neutrons need to be slowed down to cause further fission of uranium nuclei, otherwise they'll be travelling far too fast. So this neutron at the top has too much energy and will pass straight through the nucleus. This neutron has too little energy and passes away from the nucleus, so this neutron is travelling at just the right speed to be accepted by the nucleus. So the moderator works just like the coolant. It slows down the neutrons by collision. Now again, in older reactors it tends to be water, or in newer reactors liquid graphite, and if the reactor core has a vacuum surrounding the fuel rods, a chain reaction wouldn't work because the neutrons would be going too fast. Now each collision between the neutron and the moderator molecule is an elastic collision, so what it means is all of the kinetic energy, all of the momentum of that neutron is transferred to the moderator molecules. Now this is very similar to the action of the coolant, which is why the moderator and the coolant tend to be the same substance in a nuclear power station. Now what do we know? The reactor is then placed inside a steel vessel. So the steel vessel is used because it can withstand high temperatures and pressures produced by the fission events. And the steel vessel will also absorb beta radiation and reduce the amount of gamma radiation and free neutrons produced in fission events. But to further minimize this, we can surround this in thick concrete walls, and the thick concrete walls will reduce gamma radiation and even more of the free neutrons released in the fission process. So what do we know? Nuclear fission is the splitting of a large and unstable nucleus. Spontaneous fission is rare. Usually for fission to occur, the unstable nucleus must first absorb a neutron. The nucleus undergoing fission splits into two smaller nuclei roughly equal in size and emits 2 or 3 neutrons plus gamma rays. Energy is released by the fission reaction. All of the fission products have a kinetic energy and they may go on to start a chain reaction. The chain reaction is controlled in a nuclear reactor, control the energy released, and the explosion caused by a nuclear weapon is caused by an uncontrolled chain reaction. So if we've been successful and learnt in today's lesson, we can explain how a fission reactor works. We can describe the parts of a thermal nuclear reactor, and we can explain how a nuclear fission reactor is controlled. So I hope you've enjoyed today's lesson on fission reactors, which is part of the atomic structure topic in GCSE Separate Science Physics. Thank you very much for listening and have a lovely day.